In the previous lecture, we were looking at voltage growth in the CR circuit. Why? Because it was the voltage that was changing with time. So now we are going to see how current changes with time. So when you cross the circuit, when you cross the switch here, using Kirchhoff's voltage law, V DC voltage will be equals to the inductor voltage or voltage across the inductor plus the voltage drop across the resistor. Voltage across the resistor, voltage drop across the resistor. So V will be equals to VL plus VR. That is equation 1. So we look previously, we saw that for the capacitor, when charging the capacitor, we looked at VC was equals to charge over the capacitance. But then for the inductor, it will be a bit different. Instead, for the inductor, the EMF will be induced in the inductor. So the EMF which is the voltage, so VL is the induced voltage, and it will be caused by the changing current in the inductor. So VL will be inductance times change in current over change in time. So we substitute this in equation 1, and using Ohm's law, we get the voltage drop across the resistor. So we substitute IR, and this in equation 1, we get this. Then after we look at the conditions. So we look at the conditions. At the instant of crossing the circuit, the rate of change in current, is such that it will induce an EMF in the inductor, which is equal and opposite to the DC voltage. So from Lenz's law, we know that the rate of change of current in the circuit induces an EMF in the inductor. Then after that, that induced that induced EMF will oppose the current. So when it opposes this current, I will become 0. I don't know whether that is clear, but I can repeat that. So when the circuit is closed, then I flows through the circuit. When I current reaches the inductor, it will induce an EMF in that inductor. Then that EMF, it will oppose the current, so that current will become 0. So at initial state, after the induced EMF will cancel out that initial I. So I is 0, meaning that voltage cross R will be also 0. So when we substitute this in equation 1, at initially, V will depend on the induced EMF in the inductor, which is VL. So when you compare this with the previous circuit, you see that they are opposite. The previous circuit, at initially, we didn't have charge, so we didn't have VC, but we had a voltage drop across the resistor. But for this, we have induced EMF, which is VL, but we don't have voltage drop, so they are opposite. Then at time t, after some time, after closing the circuit, the induced EMF will reduce. So when the induced EMF in the inductor reduces, then current will start to flow again. So when you look at the equation here, we still have the induced EMF, though it is reduced. And we have voltage drop across the resistor. Then after a certain time, at time 2, T2, the induced EMF will continue to drop, will continue to reduce while the current increases. So when I increases, it will increase the voltage drop across the resistor. So we shall have, for equation 2, we shall have V equals to L di2 over dt2 plus I2R. Then at steady state, since the induced EMF is reducing, it will reach a point when it goes to 0. And we said induced EMF is VL. So at steady state, induced EMF will reach 0. Then I will increase. So at steady state, I equals to V over R. So you see that there is a similarity between these two, but they are opposite. This equation is what we had at initial state in the capacitor, in the CR circuit. But for the L, it is at steady state. Then at steady state, for the CR, we had DC voltage, which is V, was equals to VC. But here, that same equation, V DC voltage equals to VL, was at initial state. So I think that is clear. So we can look at the equations. Look at the equations of the curves. So when we compare when you compare the equations, you see that VC, when we go back and we compare these equations, VC equals to V was okay. VC, the equation for VC was exponential growth curve. V was changing up to when it reached steady state. But then when you compare it with this other curve, you see that the induced EMF started high, then it kept reducing over time. So when you look at the curve, the equation, you see that at steady state, it was 0. So it depended on change in time up to when it reached steady state. On the transient, up to when it reached steady state. So in the VL equation, we don't have steady state. Like we don't have VL minus the V exponential or something. I think that is clear. When we compare these two curves again, they are the opposite of the other curves in the CR circuit. The other curves were decay curves. These ones are growth curves. At steady state, initially, when the EMF was induced in the inductor, it opposed the current that was flowing in the circuit. So I went to 0. Then with time, it started increasing up to when it reached steady state. At steady state, the EMF went to 0. Then we remained with V equals to I think it was VR, at steady state. Yeah, VR. So when we look at the equations, you see that we have the steady state condition here and the exponential, the change in time and the steady state. Even here we have the change in the steady state and the change in time. So that is clear. Then we look at the time constant. Time constant tau, which is T2 minus T1, will be equivalent to L over R in the RL circuit. Then we look at an example. The winding of an electromagnet has an inductance of 3 henries and a resistance of 15 ohms when it's connected to a 120V DC supply. Calculate the steady state value of current flowing in the winding. Okay. So we have the circuit here. connected in series, the inductor connected in series with the resistor and connected to 120 volts DC supply. At steady state, we can look at the equations back. I equals to VR. We have V, the DC voltage, we have the resistance. What is the question? Yeah, the current. So we look at the current. We have the resistance, we have the 120 volts, the DC voltage. Then the time constant of the circuit. Tau in the L-R circuit is equivalent to L over R. We have the inductance here, we have the resistance. So we can look at the time constant. So the time constant is 0.2 seconds. Then the other question is the value of the induced EMF after 0.1 second. So as we said earlier that the induced EMF keeps reducing, meaning that at any instant of time, we have a different induced EMF. And the induced EMF is VL. So at time 0.1 second, what was the induced EMF? So we can use the equation for VL, which is the induced EMF, equals to V exponential T over tau. We have 0.1, I think, 1 second for time. Tau, we got tau 0.2. So we substitute it here in the equation. We have the DC voltage is 120, then we calculate and get that. The induced EMF, VL. Then the other question is the time for the current to raise to 85% of its final value. So so we can use the what? The equation so we need 85%. 85 is the same as 85 over 100. So we need I. Our I will be 85 over 100 of I. So we substitute what we have. We are looking for. Let me see the question again. The time. Okay. We are looking at the time. So we get this. Then we we get this equation, we substitute this. Yeah, you will substitute and get the answer. So that's all for transient circuits. We can look at the alternating current briefly. So what is an alternating system? An alternating system is where the magnitudes of the voltage and of the current vary in a repetitive manner. So this is the sign for SC. Then there are many types of waveforms. We have the sinusoidal waveform, we have the square wave, we have the triangular wave. Then we look at some terms. The period of a sine wave. What is the period of a sine wave? So the period is the time required for a sine wave to complete one full cycle. So when they talk about the one full cycle, they mean that one complete cycle from 0 to here is 180. From here, from 180 to here it's 360. So it's like a full circle. So it's a cycle. So a full cycle is one complete positive and one complete negative alternation. So the period is the time required for a sine wave to complete one full cycle. Then peak value of the sine wave. So the peak value can be either voltage peak value or it can be current peak value. So the peak value of a sine wave is the value of voltage or current at the positive or at the negative with respect to 0. So peak value is from here at the peak or at 90 here up to 0. Like, so you can either get a negative peak value or a positive peak value, either for voltage or current. Then peak to peak, for either voltage or current, starts from the positive peak up to the negative peak. So peak to peak is twice the peak value. So peak to peak, peak to peak is 2 VP. I think that is clear. Then we look at the root mean value of a sine wave or the DC equivalent. So the root mean square value is the same as the effective value of the sine wave. And it's equivalent to the DC voltage that would do the same amount of work. So remember, we are looking at the alternating current or voltage. So the root mean value is that equivalent of the DC voltage. The DC voltage is usually less than the AC voltage or current. So how to get the root mean values? V root mean is 0.707. But then I gave you the simple way to remember this. So you can change your calculator in radians, then 0.707 will be the same as √2/2. But the calculator must be in radians. So you can remember, these are easier to remember. So you know that getting V root mean will be √2/2 in rad times the peak voltage. Then the same applies to the root mean current. It's √2/2 peak current. Then getting peak current, when you have the root mean, you get √2 times the root mean value, either for VP or IP. So we look at the average value of the sine wave. It is 0.637. And the average value is defined as this 0.637 is equivalent to 2/pi. So I think this is easier to remember, 2/pi instead of 0.637. And we look at the frequency. The frequency is the number of cycles that a sine wave completes in 1 second. So the more cycles in a second, the higher the frequency. The less cycles, the lower the frequency. Frequency is 1/t, 1/period. Instantaneous values. These are the values of the alternating quantities at any instant of time. So the instantaneous values, they can be for peak, for the voltage or the current. So you just have to substitute here in this equation whether you need current or voltage. You just have to substitute. Form factor of a wave is the root mean value over the average value. Peak factor or crest factor is peak or maximum value over root mean value. Then we look at some examples here. Determine the periodic time for frequencies 50 Hz, B 20 kHz. Frequency, we have the period. Determine the period. We need the periods, but we have the frequency. So period will be equivalent to 1/f, 1/50, then we get 20 milliseconds. Then also this 20 times kilo, which is 1000, you get 50 microseconds. Then example 2, a supply voltage has a mean value of 150 volts. Determine its maximum value and its root mean value. So we know the mean value is the average value. And we know that the average value is the same as pi over 2/pi or 0.637 times the maximum value, Vp. So we use that equation. We have the mean, the mean value, so we can get the maximum value. Then the root mean value, we can go back here. So in the question, they didn't specify whether it's V root mean or I root mean, but getting the answers, it's all the same. We have the same constant. So we just use and get the answer. So that's all for today. Thanks for attending. If you have any questions,